Dennis Wright will be speaking on the status of necessary body of knowledge, International Space Elevator Consortium reports, the IAA and Obayashi Corporation. Dr. Dennis Wright is Vice President of the International Space Elevator Consortium, where he works on simulations of the physics of the space elevator, including its dynamics, its electrodynamics, and the effects of radiation. Dr. Wright recently retired from Stanford University, where he was a physicist in the Elementary Particle Physics Department of the SLAC National Accelerator Laboratory. He has been involved in more than 20 experiments ranging from low-energy photonuclear reactions to the ATLAS experiment at the Large Hadron Collider at CERN. Dr. Wright earned his PhD in nuclear physics at the University of Illinois at Urbana-Champaign. Dr. Wright, the floor is yours.
All right. Yes, thanks for the introduction. And you'll probably notice I made quite a career change in going from the microscopic world to the macroscopic. And there has been a lot of learning on my part in doing that kind of change. So what I'd like to talk about today is the space elevator body of knowledge. In other words, do we know enough to go ahead and start doing a development project? And I hope I will convince you that the answer is yes. What do we know today? It's a pretty big body of knowledge already, and I'll try to summarize that, although in by no means an exhaustive way. We spend a lot of our time now on finding out what will we know. So we have to think of all those vague and nebulous things called the unknown unknowns and try to pluck things out of that region and put them into the known unknowns. And a good example of that is what's been going on with the recent study we have in ISEC, which is how does the climber actually grip the tether? And so we're learning a lot about what I considered to be a rather mundane thing, that is, what is friction? And it's turning out to be a lot of unknown things about friction. We have to measure it, very little theory predicting what it should be. So a lot of the parameters for the climber and the tether material itself are sort of moving into the known unknowns. In other words, what do we want to know about them? And finally, I'll summarize by saying, or trying to convince you that we do know enough to go ahead with a research program and development. We do have a rather large body of knowledge to draw on for the space elevator. As I mentioned, it's what I'm going to present is certainly not exhaustive. I have three main sources. The International Space Elevator Consortium does studies and papers, and we post those on our website. There are many studies and papers from the International Academy of Astronautics. So that's another source that we depend on. And the Obayashi Corporation in Japan is actively developing space elevators and running tests. So let's talk about the things that we know and the literature that's out there. We have a reference library at ISEC, and that's also on the webpage. And going through that, I estimated about 600 unique entries and divided into 19 sections. And these include the ISEC study reports, and there are 11 of these so far. Lots of articles on tether materials, about 90 articles and papers. And of course, the research on carbon and strong materials has journals of its own. So there's so many things to choose from, but 90 of them so far look pertinent to us. Tether dynamics and electrodynamics, we have 88 articles there. So how does the tether move? What does the electromagnetic radiation do to the tether, and how can you transmit power and things like that? Architecture. So Fitzer talked about this, and we have 79 articles talking about the architecture of the space elevator. Space elevator environment, lots of things here. What do we do about debris? What's the effect of radiation, and so on? And then related to the architecture, of course, is what we have about the Earth port, the geonode, and the apex anchor. So we have a lot of these things that are published, available literature, and we build on these things. Now I'll talk a bit about the studies that we do. So at least once per year, and lately more than one, we have an in-depth study and consequently a report in which we cover a major item of the major space elevator issue. And these typically take about a year to do, sometimes more, sometimes less. And I'll just very briefly summarize those. You can find out a lot about these. They're all posted on the website, so you can read them at your leisure later. But to start out, we have two studies that deal with the space debris situation. So one in 2010 and an update in 2020. And they conclude that the problem is manageable. So I think Pete touched on this before. We have also two studies on the transportation infrastructure, which is quite relevant to the topics today. Space elevator concept of operations, what the space elevator will do for you. So two studies on that. Two studies dealing with the design of the galactic harbor and the space elevator Earthport. And Vern's going to tell you about those in his talk. The concept of a multi-stage space elevator is quite interesting. And so we don't necessarily have to build it all out of one tether. We can have a first or a couple first stages built out of a rather unique concept. And to find out more about that, go see the report because I haven't got time to go into that. The 2017 report dealt with our simulation needs. So how does the space elevator move once it's up there? And we have to, of course, know what kinds of forces it's going to exert on the Earthport. What do we have to do to stabilize it, to make sure that we understand all the forces and loads that go on the space elevator. So this can be done a lot by simulation, and we essentially laid out the roadmap for developing the simulator. 2016 report was for the GeoNode and Apex anchor. 2014 dealt with the space elevator architecture roadmap. So how do we get there from here? And 2013 was the first serious look at space elevator climber designs. The conclusion here was that climbers could be built mostly, I say mostly, with present day technology, and spacecraft design is a well understood art. Now, as I said, you can see all these at the ISEC website under the Resources tab and the Studies tab. We have two other studies, and I'll talk about those a little bit later. Now, the IAA, as Pete mentioned, has put out two studies, and he mentioned both of these. One is the assessment of the technological feasibility and the way forward for space elevators. So two of the conclusions there were that given a tether material, space elevators look feasible. So that was important. And also, as far as the investor is concerned, it looks like such a mega project would be successful for investors. And then in 2019, there was another IAA study, Road to the Space Elevator Era. And the conclusions here were similar to the ones at the Climber study. That is, many of the components can be built with today's technology. And the tether material is, of course, the pacing item, but as we have heard, we expect that to be coming along soon. And there are lots of IAA papers having to do with space elevators, about 50 presented at the conference, the IAC conference. And I know there are probably more than this, but my brief search showed at least 15 Acta Astronautica journals dealing with space elevators. So that's the academic world, I could say. Let's move on to what's happening in the corporate world. And here we have a kind of a unique example. The Obayashi Corporation is one of the 5 large Japanese construction companies. So they do civil construction and big project construction. They are teaming up with the Japan Manned Space Systems Corporation, and they are actually doing some tests. As Pete mentioned, they have their own design based on a 2-tether system, both made of carbon nanotubes, and they assume a 100-ton climber, whereas we're assuming 20. And all of this is under active development. I believe they are the only people in the world who are currently paid to work on space elevators. So I think that's quite an achievement. They have actually flown ISS, International Space Station missions, testing likely tether materials and even tether climber designs. So they have flown experiments. And they have published several IAA papers and studies. So we draw on that knowledge as well, especially the experimental knowledge that they are gaining. The plans for Japan space elevator, they have a detailed deployment plan already worked out. They have costing and a construction schedule, so they're estimating 100 billion, and the schedule is for 2050 construction. And at the bottom of the page, you see a depiction of their station at the GEO node, and that is basically a collection of inflatable modules that are at that position. So that's the knowledge base, my survey of the knowledge base as it stands at present, but we are, of course, increasing it. And our annual studies will continue. So we have many more important topics to look at. We have a research division. And several years ago, we went into the exercise of identifying some of the major issues that needed to be studied. And we costed them and made timelines for them. And so we basically have an idea that, given the funding, we know where to go and what to start doing in the research area. Testing. Okay, Fitzer mentioned this and emphasized this rather strongly. It's a huge part of what's going on. With a tether material on the horizon, we need to be planning specific lab tests. And right now, as Adrian and Rob mentioned, a lot of the market is for powders and small pieces of graphene, for example, but nobody is really looking at testing macroscopic pieces of this yet. And so that's a very important thing to get started. Now, let's go back to some of the current studies. As you heard from Jerry, the most recent completed study is the Green Road to Space, and he told you all about the evaluation of the environmental impact of the space elevator and the big advantage that it has over rockets. So that is in final review, and it's available on the website. And the study that I mentioned, it's going on now, has to do with the climber tether interface. So in 2013, there was a climber study in which they looked at various types of climbing technologies and how do you get the climber to grip the tether and so on and so forth. And there were lots of really ingenious methods put out. And in the current study, we think we have ruled out pretty much all but one, and that is the pinched wheel design. So we'll have a tether, and as you can see by the diagram, the purple cylinders are pressing the tether from either side to produce the friction force that allows the climber to be advanced. And one of those unknown unknowns, which now we think is a known unknown, is that we are quantifying the parameters that are impacting friction. And one thing we didn't really effectively appreciate until now is that now that we've gone to a pinched wheel design, we really need to pay more attention to compressive forces. So we're always worried about the tensile strength of the tether, and that's of course critical. But the tether itself has two jobs. It has to be strong enough to support itself, but it has to have a mechanism that allows gripping. And it looks like single crystal graphene may be rather slippery. And so we have to understand very well what the coefficient of friction is and how to increase that. And we think we have a way to do that, but we have a lot more to learn, especially when it comes to this interesting idea of molecular engineering and how we can modify sheets of graphene to stick together in a strong way and not delaminate as these climber forces are applied. So that's the current study, and it's going on. It may go on for longer than a year because we're finding out lots of things that we need to look into. Now, the research program, as I've mentioned, is pretty well laid out, and a lot of the materials, or a lot of the areas have been identified. So tether dynamics, as I mentioned, electrodynamics, radiation effects, the multi-stage space elevator, space debris, climber engineering, and space elevator simulation. So as I mentioned, we have, these are costed, we have personnel estimates completed. We even have Gantt charts. So we know pretty well what we need to do, and we are ready to go upon some funding. So research is there. And testing. Adrian showed the picture of the samples that we have from general graphene. And so I think that's fascinating as well, that, that you can actually see a monolayer of polycrystalline graphene. Now, this is interesting because in our study, we are trying to find ways to test materials that we don't have yet. And polycrystalline graphene is a kind of a prototype. It's not quite the single crystal graphene that we want, but it might be good enough to start doing testing on it to give us some idea not only of what single crystal graphene might be like, but also to give us the experience of developing the tests and the material, the equipment that we need to do the tests. So practical questions are, how do you take a monolayer off the substrate without destroying the monolayer, and so on, things like that. How do you make a tensile strength test, or a brittleness test, or a compression test? So all of these tests are in the process of being identified, and the next step will be for us to probably work with people like General Graphene and Adrian and Rob, and trying to devise the equipment that we need to do the testing. So we need equipment, devising the tests, planning the tests, and much of this is underway. Another part of the testing, which is quite a bit different from the sample testing of the tether material, has to do with prototypes. And as I mentioned, Obayashi and JAXA are already doing prototype testing with climbers and tether materials, so that's great. A very interesting thing is happening with the multi-stage space elevator that I mentioned. So this is an alternative way to enable the construction of the space elevator using present day materials. So if we can build a multi-stage space elevator, then we don't have to wait for those materials. But a prototype, a 5-meter tall prototype, is being built in Panama to demonstrate the principles of the first stage of this multi-stage space elevator. So once again, I encourage you to look at John Knappman's, he chaired the study for this in the 2018 report. So please have a look at that. And now I'm to the end, and do we know enough? A lot of the work has already been done, and we've answered some of the big questions. So see the ISEC reference library and refer to the talks that you've heard earlier today. We have a very good idea of what we need to know. So we have a proposed research program. We know we need to do lots of lab testing, and we're on our way to defining what those tests should be. We will lean heavily on the testing already done by ISEC, Obayashi, the multi-stage testing. And based on all of this, I think we are really ready to start a development program. That's all for me.
All right. Thank you, Dr. Wright.